back to HackCode. In this video is solving the maximum subarray problem, which is a commonly asked interview question that tests our understanding of array manipulation and optimization techniques. This problem asks us to find the contiguous subarray within an array which has a larger sum. So let's dive in. So the question is, given an integer array nums, find the subarray with the largest sum and return its sum. So example, here for given array, the maximum sum is 6, so which comes from the subarray. So example 2, here the subarray 1 has only one element, and hence the largest sum is 1. So coming to third example, we have subarray is this one, so on adding it we get the largest sum, which is 23. Every element adds to the value of the largest sum here in this case. So constraints are num's length is in the inclusive range of 1 to 10 power 5. So indicates that we should be solving this in O of n or O of n log n. So we can, but we can solve this in O of n only. So we don't need to even think of n log n also. Why? The reason why I said that O of n is only feasible because when we go for n square or more than that, the number of computations per second is 10 to the power of 10, right? So which is not feasible for a given processor these days. So only up to 10 power 8 or 10 power 9 computation can be done per second. So let's look into the question and understand this. So first, what's subarray? A subarray is a contiguous part of an array. Unlike subsets, which consists of non-adjacent elements from an array, a subarray must contain only the order of elements as they appear in the original array, and it must be made up of the elements that are adjacent to each other. So to understand this, let's go over the array here, ABCD. So the subarrays could be A, AB, ABC, ABCD. So these are starts from A. So starting with B, BC, BCD. So similarly for C. So for example, if you have an array of 1, 2, 3, 4, then 2, 3 is a subarray, but 2, 4 is not because it skips 3. Hope you got the point. So let's solve this question. So first approach is we have the brute force. So we explore every possible subarray by calculating the sum and keep track of the maximum. So while this is a straightforward, this method might not be efficient for the large arrays because it has a time complexity of O of n cube. But let's look into the method. So this is how we initialize the maximum as nums of 0, and then we keep track of how many elements in the array in the length of nums and captured in variable n. So we tried over the two loops here. So remember here we're doing I for j in range I, because I is as we seen in the other case here example, A is also a subset of the ABCD, right? So to cover that cases, we start j with I. So here we're taking the current sum is equals to sum of nums of I to j plus 1. That is, we are including sum till I to j plus 1, because like Python computes here exclusive of the last one. So when we include j plus 1, the sum is included till nums of I to j. That's why you do j plus 1. So max sum is, at this point we have max of max sum to the current sum. So this is just like taking the local maximum, like just like greedy here. So here at the end we return the max sum. So here the time complexity is O of n cube, where n is the length of the nums, and space complexity is O of 1. So why n cube? Only two loops here, because we have sum. This also does O of n operation, right? So it's like 2 loops here and n here, so it's n cube. So next approach is using Kadane's algorithm. What's Kadane's algorithm? It checks each number and decides whether to add it, adding into the current sum benefits us or not. If it doesn't benefit, it starts a new sum. So this brilliant yet simple logic brings down the time complexity to O of n, making it vastly superior for the logic results. Let's look into the code. So similarly here also, we initialize the maximum and current sum to the nums of 0, and then we start with the first element, iterating with the first element of the nums. With the first index, not the first element. So here Since this, as we discussed, this algorithm checks if adding each number benefits us or not. So this is the point where we check. So current sum is equals to max of num and current sum plus num. So it could be that if adding, there could be cases where adding this num would be to the current sum would be the benefit, or else not taking the previous sum and considering the new array from here with benefit. So in those cases, we would filter it out here, and then same here, max sum is equal to max of max sum and current sum. So at the end, we return the max sum. So here the time complexity is O of n, where n is the length of nums. So and the space complexity is O of 1. So let's look into the demo. I've got the code added here. So let's try executing brute force. It's an accepted solution, but this test case is very small. But let's try submitting it. It would give TLE, that is time limit exceeded error. Since it's O of n cube, which is what 10 to the power of 15, it's not at all feasible. So yeah, it's TLE. And now let's try with the Kadane's algorithm. So yeah, it's accepted. And let's try submitting this. So yeah, it's accepted solution here as well. So conclusion, understanding these two methods not only helps in solving this problem, but also appreciating the beauty of optimization in algorithm design. So the brute force method teaches us about the problem space, while Kadane's algorithm shows how dynamic programming can lead to a significant improvements. So whether you are a beginner or an experienced coder, mastering these approaches can greatly enhance your coding skills in coding interviews and competitive programming. Thanks for tuning into this episode of Hacker. If you found this video helpful, be sure to give it a thumbs up and subscribe to the channel for more coding.